Hello, we're group 14 and we did the bicycle information system. I'm Joseph Gardner and I'll be presenting with Peter Kroger and Benjamin Hinton. So for today's agenda, we're going to cover the abstract of our project, the overall background of it, then the design, the hardware design, the software of our project, the Gantt chart we used for planning, our budget, and then finally the conclusion and the results we learned from our project. So for the abstract, the design of the bike information system, we wanted to make calculated distance, speed, and angle of inclination. And then it displayed those values via the LCD screen on the front on the handlebars. And in order to display these values, we utilized an accelerometer, a Hall effect sensor, an LCD, and the PIC16 kit we were given. And then we tried to minimize the total cost of all the parts so we could easily replicate it in the future and it could be mass produced. So the objectives that we set for ourselves to meet was to obviously create the bike information system that measured speed in miles per hour, enable it to track the total distance traveled by the bike, and then make it easily compatible with almost any bike setup so anyone could just put it on their bike and it would work. As for the background of our project, after doing some research, we found that devices for tracking distance and speed on vehicles have been developed since around the late 1890s, but modern cycling computers weren't in use until around the early 1980s. And things like computers and GPS help enhance the capabilities of the device, allowing you to see more information and get more data out of it. And some of the first cyclocomputers simply displayed the speed that the bike was traveling, but eventually other features such as like GPS, heart rate monitor, power meter, and other stats that cyclists are interested in were implemented into systems, and we wanted to create a system that displayed some of those things. As for the overall design, we essentially put our Hall effect sensor right on the outer rim of the bicycle with the magnet being on the outer rim and then our Hall effect sensor being attached to the frame. So every time the wheel passes it, the magnet would go by the Hall effect sensor and send that data to the microcontroller, which we had mounted on the front frame right underneath the handlebars. And then right above the microcontroller mount, which we put in a little box, is the LCD, which would display the various values like speed, angle, and overall distance traveled.
For the hardware implementation, overall we utilized 10 of the 12 available pins on the Pickett Lin demo board. The remaining 2 pins, we were able to use the LEDs that were associated with those pins in order to do some testing, but other than that, they remained open. Another thing we did with our hardware was we placed the Hall effect sensor as far away as possible from the rest of the system to minimize noise. This was able to give us more accurate and clear readings whenever we were getting values from the sensor. Furthermore, we use the Hall effect sensor to get input and calculate speed and distance, and we place an accelerometer in our system on a large breadboard so that it would be level during its initialization, and it could give us more accurate readings. For the software implementation, we use MPLAB XC8 to compile and program our PIC microcontroller, and to test this code before programming it to our hardware, we utilize Proteus to simulate this microcontroller within the code or with the code. This allowed us to do a lot more testing, a lot more fast or a lot more quickly, and ultimately achieve our goals a lot faster. So the simulation software is definitely helpful for that. We interface with the accelerometer using an analog to digital conversion. With the accelerometer that we used, the ADXL335, we were able to take 3 analog inputs from each of the 3 axes, the X, Y, and Z axes, and convert it into a digital signal, which we could then use to get the tilt of the axes relative to the bike. We interface with the Hall effect sensor as a digital input, This was just so that we could count the number of revolutions that the wheel has made using the Hall effect sensor, and it would give us a pretty accurate distance calculation based on the circumference that's input to the system. Finally, we wrote to the LCD screen in 4-bit mode. Doing it in 4-bit mode as opposed to 8-bit mode saved us a lot of pins on the hardware side, so it allowed us to fully use the accelerometer in all 3 axes and still have a couple pins to spare afterwards. Some changes that were made to the hardware and software as we went through this project were that we originally had an LIS 3DH accelerometer, but we replaced it with an ADXL 335. This is just because it was a little easier for us to implement on the software side, getting it to communicate with the PIC. The LIS 3DH used SPI interfacing, which we had some issues getting to work properly with the PIC. So using the ADXL was a little bit easier for us because we had previous experience converting analog to digital signals. Another thing was the code, obviously from the LCD, was changed to 8-bit or from 8-bit to 4-bit mode, which greatly helped us on the hardware side. And finally, the accelerometer was mainly used to track the angle of inclination rather than the actual acceleration. We just felt like this was a more useful stat for the user to see as they're riding the bike.
So for the results of our project, firstly, we met all of our project objectives, and all of our sensors in the end ended up working and went together well to create our working prototype. We achieved a consistent output to the LCD, and then our big next steps would be to work on the form factor and the packaging for the device. Right now, it is not in a state where it could be easily mounted to a bicycle in a safe way where it would be protected from all the elements. Here's our Gantt chart. It has been revised while we were working on the project to stay in line with various difficulties that we had. Chief among these were LCD functionality validations. When we used our first LCD that we bought, we had a lot of trouble just getting it to work. And in the end, we found that it was just a faulty LCD. And when we replaced it with a brand new one, the brand new one worked fine with the code that we had already been attempting to try on the old LCD. Here's our budget. As you can see, we were well below our budget projections of $100. We came in at $53.68, although this does not account for the fact that this is only a prototype model, and were we to make these bike information systems in bulk and buy all the parts in bulk, our prices would be significantly lower. So in conclusion, we successfully displayed speed, the angle, specifically the pitch of the bike, and the distance to the user. We learned a lot about product design and building a prototype. We combined multiple sensors / the LCD to make a cohesive project, and we will be taking many lessons learned from this project to help in future work in our senior design and onward into our careers. Some examples of these lessons are, chief among these examples is going to be using the data sheet for each individual device to the letter. We found that had we really dug deep into the data sheets, it would have been very helpful. Not just the PIC data sheet, which we'd been using all semester, but especially the LCD and accelerometer data sheets. They had lots and lots of useful information. And here are our works cited. Thank you.